Okay, so we're going to start now talking about another oscillating system called the pendulum. But before we get into that, I want to just briefly go back to springs and the energy of springs because there's one thing I forgot to mention. So we have this spring system. Let's say it has a mass of 0.5 kilograms. Let's say the K value is 100 newtons per meter. Okay, so what would be the period of this oscillating system? Okay, so we get a period here of 0.44 seconds. Okay, so the question I have for you is, what would be the period of this system if we were floating in space? Or how would the period of this system change, rather, if we were floating in space? Or maybe if we're on the moon? How would that affect the period of oscillations here? The answer is it doesn't, because the period of the oscillation of a mass spring system is completely independent of gravity. Okay, but now we're going to look into a system that actually does depend on gravity, and that is the system of an oscillating pendulum. Okay, and so here we have an example of a pendulum, and instead of a spring force causing oscillation, we have the gravitational force. Okay, so we have at the peaks gravitational potential energy, and then at the lowest point all that gravitational potential energy has been transformed into kinetic energy. Okay, and just like for the period of a spring system, we can actually calculate the period of a pendulum using a similar formula. So let's go ahead and draw out a pendulum, okay? So when this pendulum, the thing that causes it to oscillate, instead of looking at forces here, we're going to look at torques, okay? And so there's a gravitational force pulling down on it, causing a torque, causing it to rotate, and it's going to depend on partially on what this angle is, okay, for the amount of torque. And so what happens here is that there's a relationship between torque and angle, and that relationship is maxed out when the pendulum is at perpendicular, because that's when it has the maximum torque, and the force and the radius are perpendicular. Okay, so in this case though, we're going to be looking at this system where we have the force of gravity mg causing a torque. We have some angle away from the equilibrium position. It would be equivalent to that angle right there. Okay, and now remember that the condition for simple harmonic motion is that A is equal to negative omega squared x. Alright, in this case, instead of A and x though, since it's an angular oscillating system, we're going to use alpha equals negative omega squared theta, our angular measurements. Now we're going to try to make it look like this so that we can find out what omega is equal to, because once we know that, then we can write our period formula. Okay, so let's start by setting up a net torque equation. So for this system, I alpha is going to be equal to the torque, negative mg, times the length of the pendulum, L, times the sine of the angle right here. Okay? Okay, so now we're going to say, well, if this is a massless string, then the moment of inertia for this rotating system, I, would just be mr squared, where r is equal to L. So ml squared alpha equals negative mg L sine theta. So we're going to solve it for alpha. Looks like m is going to drop out of the equation. We'll divide by L squared and get alpha equals negative g over L times sine of theta. Okay, well we have a problem here, right? Because this is not what we're looking for. We want it to look like this. Okay, but we have this sine theta here instead of theta. Okay, well make sure real quick your calculator's in it. Put your calculator in radian mode, and I want you to find out what the sine of 0.01 radians is. Hopefully you found that that was about 0.0099998 something, or 0.01. Now what about sine of 0.1? Go ahead and find the sine of 0.1. Hopefully you find that it's about 0.0998. Okay. Sine of 0.2 would give about 0.1986, which again, really close to 0.2. Okay, this one was really close to 0.1. So what happens is, when theta is really, really small, okay, when it's close, well, let's just say when it's much smaller than 1, okay, that sine of theta is approximately equal to theta. And this is also actually true of tangent of theta at really small angles. Okay, which means that alpha, if the angle is really small, is equal to negative g over L times theta. Okay, which means that omega is equal to the square root, or rather, omega squared is equal to g over L, or that omega is equal to the square root of g over L. I'm going to remind you how I made that jump. If we can write it like this, and this is the condition for simple harmonic motion, that means that this piece right there would be equal to this piece right there. And the reason we want to do that is because that's how we can connect it to the period, 2 pi over omega. So then the period of a pendulum would be equal to 2 pi over the square root of g over L, which can simplify to t equals 2 pi times the square root of L over g. And so the condition for using this formula is that, remember that theta needs to be very small, okay? So for small angles, and when we say small angles, really, probably like if this is about 20 degrees or less, then this formula is a pretty good model for the period of the pendulum. Okay, so what would happen to a pendulum's period if we were to make it really, really long? How would that change the period of it? Well, the bigger the value for L, then the bigger the value for T, the longer the period. So the longer the pendulum, the longer it should take to complete an oscillation. Okay, and we can see the other factor that affects the period of a pendulum would be the strength of gravity. So let's say that we're designing a clock that has a pendulum, which is like a grandfather clock, and we want it to swing once each way every second. So 1 second, 1 second. Okay, what would be the period of this pendulum? It would be 2 seconds. 1 second there, 1 second back, 2 seconds. Okay, so what I want you to do is find how long this pendulum would have to be in order for it to have a period of 2 seconds. Well, 2 seconds equals 2 pi times the square root of L over G. Okay, we're going to divide it by 2 pi, so 2 over 2 pi equals square root of L over G. We'll square it, equals L over G, and then multiply up G. So 2 over 2 pi squared times G equals L. And so in this case, 1 over pi squared times G equals L. And you get that L is about equal to 0.99 meters. Okay, so almost 1 meter to have a pendulum that oscillates 2 seconds. Okay, and so you might see those big grandfather clocks, okay, the big clock, face, right? And then there's the big pendulum hanging down. Okay, and the reason it's so long is because it needs to be about 1 meter for each swing to be 1 second and have a total period of about 2 seconds.